This lesson's called Composition of Functions, and I must be honest that it'll be difficult to see why we need this. And I'll try and allude to it during the lesson, but it might be a little difficult to understand why we're going through and performing this breaking up of functions. But I won't say it's that difficult though. But don't get excited that somehow something difficult's about to happen here, because actually we've been doing composition of functions all the way through. We just didn't call them that. Here it comes. When we look at composition of functions, we are looking at one function inside another, or one function followed by another. So before I get into the notation that might cause your brain to just get a little confused about what's happening here, let me show you an example of a composition of functions. If I made a function f at x equals log of x squared, that's a composition of functions. It's got x squared inside, and then you got to do log on that, and you know how to do this. If I had to put this on the last test, you wouldn't have been overwhelmed by it. You would have said, okay, if you put in a 3, for instance, that means first you're going to square the 3, and then you're going to sub it in there. You're going to go, okay, so x squared. Okay, squared 3. Oh, that's 9. And then you're going to do log of 9 and get that answer. Okay, so it's really just a function followed by another function, 2 things in a row. So this is where I allude to why you might want to do this. In calculus, we'll want to analyze what this function's doing, g, and what this function's doing, f. We want to analyze those 2 things separately, so we might want to pull these apart. That's all we're talking about here in calculus, is breaking a 2-part function into 2 pieces. All right, there's my calculus part of the speech. Here's the new notation. When it's a composition of functions, you'll see this. F with a circle, it's a circle, and then a g. A new notation. So if that looks weird, well, it's just because it's new. And it's called, it looks like fog. Everybody calls it fog. In calculus all the time you hear people say, oh, do I have to do fog on this one, Mr. Todd? I'm like, yep. That's, and then I just say yep, and we all just call it fog, even though that's not an O. It's just a circle. And but here's the important part here, and I'm underlining this in red. You have to know that f o g means f at g at x. And if you're looking at f at g at x, you're like, that's too many letters for me. Don't worry, I'm going to show what f at g at x means along the way. The important thing at this point is there's 2 ways to write composition. F at g with a circle, or f at g at x with the g at x inside. Oh, what's the meaning of this whole thing? Oh, the circle. Just this. That's exactly what it means. And it has other applications, so it's not like, oh, it's just a one lesson throwaway thing. Later on, we'll use that symbol to mean in different situations. Anyways, this is read f at g at x. There are 2 important points here. First, by looking at the notation, it becomes clear that g will act first on x. That is, if I sub x in there, g is going to work on it first and do its operation, just like in the log x squared question. The x squared operated first, even though it wasn't the first one written. It was the second function written, but it's the first one that gets to act on x. And then f will act after that, so g acts first. And this is the picture that really shows what's going on. You take your input number, you put it into g, you do whatever you have to get the answer there. Here I squared to get 9. And then f takes that number that you got out of g and does its action on it, and then you get your final answer. Just a 2-step function is all we're talking about here. The function g acts first, then sends its output to f as an input, then f acts. Well, there's one little difficult thing on the next slide. And before I get there, I just want to explain that. If this is going to work, it means that whatever the outputs of g are better work as the inputs of f, or we're sort of stuck. What I mean by that is, if g were to produce a negative number, and f is square root, well, that's not going to work out too well, is it? So we have to just take a look at that and make sure that the outputs of g can be inputs of f, or this whole process doesn't work. You're like, well, what do I do if it doesn't work? Well, same as what we did before. We said domain x can't equal 2, x can't equal 3. We faced that situation before, so not a big problem, really. So that's all this is saying. The domain and range of f at g. The composition of 2 functions exists only where the range of the first function overlaps or is contained in, and that's all just fancy words for saying it better work. The outputs of g better work as inputs of f, or this whole process is off for those x values. So the domain of f at g is a subset of the domain of g. That is, you might get all of your domain in there, but you might not. and the range of f at g is a subset of the range of f. You might get the full range of f, but you might not as well. Okay? We're not going to get too carried away with that. That's just mentioning this. We'll follow up on that in calculus once we get a little farther with this. So, in words, if the input of f is the output of g, then the whole thing only works when the range of g matches up with the domain of f. And I'll do some examples to show off that. I'm going to blow this up a little bit because I can't see too well, and I'll just scroll down as we go. Here's the examples. Way back to something we haven't used much of since chapter 1, this mapping notation. It's supposed to be simpler. Instead of doing a whole equation and a huge table of values, let's just talk about some individual points. F takes 1 and turns it into 3. Or it takes 2 and turns it into negative 4, 4 into 7, 5 into negative 4, 9 into 3. This is the only things f does. So we're not doing the whole equation. If you want to know, if you plug a number into f, what happens, you just look at in here and see what happens to it. And there's g. G goes 1, 2, 3, 0, 7, 1, 9, 9, 10, 3. And this says find f at g at x. Find all the possibilities here. Okay. Step 1. Think about g at x. What can g do? Because g is going to act first. Well, f at g at x. G, well, that wasn't too pretty, was it? There we go. G can take 1 and turn it into 2. And if we were just talking about g, that would be the end of the discussion. 1s become 2s. But then f takes over and says, okay, take that 2, and what does g do with it? Sorry, what does f do with it? It takes 2 and turns it into negative 4. Now I'm unhappy with that color coding. I'm going to go with red both times. So here's what's happened. F at g at x says, okay, I can take the number 1 and turn it into 2, and then f takes over and turns 2 into negative 4. The end of the whole process is that f at g at x takes 1s and turns it into negative 4s. Along the way, it became a 2 for a little while. Couple of confused looks. Let's go back to here, to my opening log of x squared example. 3 got plugged in there, became a 9, which became log of 9 when it was all done. There was this intermediate step. See, 9 was only part of the answer that we got here. And maybe I need the decimal answer to prove what I'm talking about. So I get out my calculator, and I press log 9 here, and I get 0.95. I'll even do a couple decimal places. Do you see? 9 was sort of lost in the process. The answer isn't 9 anymore. It's log of 9. That 9 has disappeared in all of there. It's part of the answer, but it is not in the answer. Whereas here, see, same thing happened. 1 turned into 2, then f took that 2 and turned into negative 4, and there's no 2 that appears there because the 2 has been turned into negative 4 along the way. Let's do another one. G can take 3s and turn them into 0s, and then you go over here and plug 0 into f, and you go, oh, f can't handle 0. There's an element in the range of g that isn't in the domain of f, so we just don't use it. We can just leave it off our list, and we don't have to do it at all. This happened before in chapter 1. Remember, we go to add 2 points, and one of them was missing, and we just left it off the list. In math, that's what we do. If it's not there, we can't use it. We can't estimate. We can't make up something. We can't do anything with it. In the real world, would it be like that? Oh, I don't think so. Let's say you were missing a month of data from a business. You say, well, what were your profits last month? They go, well, we don't have it figured out yet. You could probably estimate. You could probably get last year's numbers. You could probably get them to share something. Hello? No, he's not. No.
No. Okay, thank you.
Okay. So in the real world, will we just leave it out like that? No, sometimes we might have more information. But in math, we just leave it out. If it can't be done, we just go, that's not going to be in my list. You can't take 3 and plug it into G and expect to get something out of F because it won't be able to handle the 0 that gets punched in it. Let's do another one. 7, 1. So G turns 7 into 1. But before it's done, that 1's got to get plugged into F, and it turns it into 3. So 7s become 3s. They were 1 in there for a little while. It became 1, but then it became something else by the end of the process. This one, 9 to 9. Okay, 9 becomes 9. Oh, that just stayed as 9. Okay, that's all right. And then over here, 9 becomes 3. So f at g at x takes 9s and eventually turns them into 3s. Last one. Take 10 and turn it into 3. 3 is not on the list of f. So I can't take it through the process. This is the only things f at g at x can do. It can turn 1 into -4 eventually. It can turn 7 into 3 eventually. And it can turn 9 into 3 eventually. And that's that subset thing they were saying on the last page. You don't get the whole range. You don't get all the outputs. You don't get 3, -4, 7, -4, 3. You only get -4, 3, and 3. You only get those 3 possibilities out of there. Any questions there? If you're sort of with me going, so you just do 2 in a row? The answer is yes. That's all composition means, is do 2 functions in a row. Oh, here's an algebraic one. Algebraic ones are good. So they want g of f and f of g. I've got to do both. So sometimes you'll hear calculus people saying goff or fog. And it's not an O, but I don't know. We all say it like that, so I guess it's okay. So let's talk about goff first. Here's the big thing you got to know about goff. Goff means g of f at x. It means take g and sub in f. And if, as I say that sentence, you're like, what are you talking about? What do you mean sub f into g? Where are you getting that from? Well, I got to go to a new flip chart and just talk about this for a second. I'll just make up a function and we'll sub some things into it so we know what we're talking about, okay? Let's say I had f at x equals 9x squared minus 7x. Now let's pretend one of your friends in grade 11 came to you and said, hey, we did this in grade 11 math. I'm getting ready for my exam. It said f at x equals 9x squared minus 7x, and I want to do f at 2. I want to sub in 2 to this thing. What does that mean when it says f at 2? I mean, what would you, if you really broke it down into words, what would you tell your friend to do? Make the x 2. And I'm just going to add a couple of words. That is, wherever you see x, write 2. Yeah, so we mean 9 times 2 squared minus 7 times 2. And then from there, you just work it out. You go, okay, well, 2 squared is 4. And I get 7 times 2 is 14. 36 minus 14, 22. Something like that, yes? I'll do it with g now. G at x equals 5x cubed plus 2x. And if I said find g at 1.3, what would you tell your grade 11 friend to do? Is it getting repetitive? I hope so. I hope this gets so repetitive that when I go back to the other page and do it again, you're like, okay, yeah, I get what you're saying now. Okay, g at 1.3, you'd tell your grade 11 friend. You'd say wherever you see x, write that number right there. And the number's got a little more complicated here, 1.3. But wherever you see x, write 1.3. And I'm not going to finish this one off because then you'd say, okay, and then you're okay from there? You're good now? You can figure it out from there? You wouldn't say much more than that. That's the important step there. Wherever you see x, write whatever's in here. He said ominously. Back to here. Wherever you see x in this g, write f at x. Oh, what's f at x? F at x is 2x plus 3. Right there. F at x equals 2x plus 3. That's red underlining, not my red highlighter. You know what I'm talking about? I'm about to red highlight a question. Coming up in a second. It's going to get the red highlighter. Okay, here we go. Okay. Well, let me say my sentence from the last thing. Look at g, and whenever you see x, write this. So it's 5, not x, 2x plus 3, plus 1, and then the bottom is 2 times 2x plus 3 minus 3. And if you're having trouble with that, I'm going to actually change colors. I'm going to just erase what I subbed in there and write it in a different color so you can really see the contrast there. My subbing. Here's the subbing, 2x plus 3. It said put 2x plus 3 into the function. So I put 2x plus 3 into g at x. See? There's g at x. Every time I saw x, I wrote 2x plus 3. And then well, do whatever you do after that. You know, like, that's what you said to your grade 11 friend a minute ago. Let's see, 10x plus 15 plus another 1 is 10x plus 16 on the top, 4x plus 6 on the bottom. There's g of f. Then from there, you might get an x to sub in. You might say, okay, now into your g at f, sub in a certain x value. Okay, let's fast forward to calculus a little bit. Like, why would you want to do this? Seems like a lot of work. Well, instead of now having to go take my input and sub it into here and figure that out, and then take it and sub it into there and figure that out, it's all in one piece and maybe a simplified piece. So calculus is good. We're going to spend a lot of time seeing, can we make this whole thing simpler? And by subbing f into g, we hopefully have simplified the process down, making it less operations. Well, if that's completely confusing, don't worry, because now I'm going to turn around and I'm going to do it the other way. I'm going to do f of g. I'll keep saying it properly. I'll try not to say fog, because we're really not supposed to say that, even though we do all the time. But, all right, f at g. My microphone falling apart here. Yeah, fog is nice. It's good. Here's the part you have to know. F at g means f at g at x. That's what that notation means. And g at x is this mess. 5x plus 1 over 2x minus 3. And then your brain seizes up for a minute. You're like, so f at, what could that possibly mean? And you've got to go back to a simple one like here and say, okay, what do I do? What does f at something mean? It means take whatever's in the brackets, whatever's in the f there, and put it in wherever you see x. So here, it's really complicated. I got to write down f, which is 2. I'm going to make a mistake here. You ready? I'm going to do it in green. 2x plus 3. There's f at x. But that said, don't write, wherever you write cx, don't write x, write what's in the brackets here. So get rid of that. And in green, write what's in the brackets there. In green, there we go, 5x plus 1 over 2x minus 3. And I'm actually not going to do any simplification there because I want you to be able to look at that and see it. I'm not even sure what the right simplification would be here. Maybe a common denominator between these two. I'm not sure. I'm not going to get distracted by that. I want to focus on, I've taken this g at x and I've put it in there wherever I see x, in the hopes that things will get simpler. If you're not convinced that things are getting simpler, I totally agree with you. Until we start using this in calculus, you won't really see why this makes things simpler. Questions there? All right. Here's an important example. Question, Georgia? It is just subbing, yes. Sub the, yeah, and really it was at the start, right? This isn't log of x. I put x squared in there and said it's log of x squared, making it all one function like that. Yeah? Here's an important example, which I'd like to highlight in pink. I would highlight it in red, but sometimes the red makes it so you can't barely read this. So I'll just, I'll get a large pink highlighter. Fuchsia. That's right. Salmon. You like it? All right. We're going with orange. Highlight orange. The biggest highlighter I have. Oh yeah. It's good. Huh? This is the one you want to understand going forward. Yeah? If f at x equals 1 over x and g at x equals x squared plus x minus 6, determine the domain of f at g at x. And here's another way to write it. It's pretty much the same. And this morning somebody asked me, why would you write f at g with an x there? Well, it's the difference between writing f. You know, I can talk to you and say, oh, let's talk about the function f, and I write it like that. Or you could write f at x. You could put an x in there, and it doesn't really change our thinking. It just lets you know the variable we're going to be talking about is x today. So f at g at x, here's the part you got to know about this notation, is f of g at x means the same thing as just f at g. It means f at g at x. Now, if I'm going to find the domain of this thing, I got to know what the function is. I'm telling you, finding the domain of this thing is not going to be a problem once I know what the function is. You guys have done a lot of domain stuff for the last few months, so you know how to find domains. If I have the function, but right now it's not a function yet. I need to go f at g at x. So what do? I look at the function f and I sub in g at x wherever I see x. There's g at x. So here comes the function. F at x is 1 over x, but my x is this whole thing, x squared plus x minus 6. That's what's in this lesson, subbing one function into the other. And once you get there, hopefully you're home free. Hopefully. A little review here of Unit 5. The domain of this thing now, to get the domain of this thing, I probably want it in factored form. And now I'm ready to state the domain. X element of reals such that x can't equal -3 or 2. Those are the restrictions on this function. What we're saying is you can't take -3 and sub it into g because you'll get 0. And then f will try to do 1 over 0, which it can't do. But do you see how it's simpler to analyze this than to try to follow through on what I just said there? So let me say it again, what you have to do if you don't do composition. You have to say, okay, if I put 2 into g at x, I'll get 4 plus 2 is 6 minus 6. I'll get 0, and that won't be allowed to sub into f because that would be 1 over 0. When it's all one function like this, then I can just look at it and say, okay, what x values will not work here, and you still can't divide by 0. Do you have any questions about that very important highlighted in red/orange example? Let's do another one that's a little simpler actually, but also gets the orange highlighter. It says if p at x equals 3x minus 5 and q at x equals 2x squared plus 7x minus 4, find p of q of 2. So 2 is the number we're going to sub into it. Now you could do this question by subbing the whole function q in there. And that's what I'm going to do. I'm going to do this 2 different ways. Let me just scroll this down. 2 ways to do this question. Oh, I'm out of scrolling. Okay, hang on. I have the technology. Going to buy myself some space here. Those of you who are doing this on paper can be amazed by what I just did. Those of you who are working on an iPad are not impressed with what I just did. You guys do that all the time. You're like, whoop, whoop, resize, move it up there, no problem. In fact, my son, all his notes are real tiny like this. When he's all done, he scrunches them up and puts them up in the corner. A week's worth of note on one page, and he just zooms in on the parts he wants. I don't like it, but he does. All right. 2 ways to do this question. Okay, ready? Draw a line. The easy to understand way first. I don't think it's better. The easy to understand way. What I'm going to do is I'm going to find q at 2. See, p at q at 2 says take 2 and plug it into q and get your answer and plug it into p. So q at 2, I just go, okay, 2 times 2 squared plus 7 times 2 minus 4. I've just subbed 2 into the function q. And what do I get here? 8 plus 14 minus 4. Maybe with your fancy calculator, you don't even show all those steps. You just bang, plug it in and go. Let's just make sure it's right before I go to the next step. Subbing in 2 to q. 8 plus 14 minus 8. Yeah, I like it. So I took 2, I subbed it into q. That's not the end of composition. Composition that says take that number, 18, and now plug it into p. Confused? Let's go back to the original example again. That's what the initial one did. Log of x squared said take the 3 and square it, then take that answer you got and plug it into the next function. The result of x squared got plugged into log. So my result here, whoop, where'd I go? Oh, I got scrolled up, did I? Back to here. So p at 18 is 3 times 18 minus 5. And I put the brackets in the wrong spot there. 3 times 18 minus 5, which is 49. 3 times 18 is 54, minus 5 is 9, 49. Okay? That's one way. I think that's the easy way. When you're first learning about composition, that's the easy way to do it. This says, take 2, plug it into Q, put your answer into P. That's the whole lesson in a nutshell. The other way to do this is actually make the function P at Q at X first. P at Q at X means take P and sub in 2x squared plus 7x minus 4. Actually sub in the Q function into P. And so that means I get 3 of these 2x squared plus 7x minus 4s minus 5. Do what you have to do to simplify that out. I think I get 6x squared plus 21x minus 12, and then the minus 5 out there. There, now I've got P at Q at X equal to 6x squared plus 21x minus 17. There's P at Q at X. All simplified down for me. Then, if I want to do P at Q at 2, I don't have to go through 2 steps like this. I can do it all in 1 step, is just put 2 into this new function I've created. And hope I haven't made a mistake here. Wouldn't that be frustrating? Okay, 6 times 2 squared plus 21 times 2 minus 17 equals 49. I get the same answer. So that's just the other way to do this question. I have no preference in advanced functions which way you do it, whichever way makes sense to you. If you're like, but if you're staring at this one going, if it was just one number to sub in, I think I'd do this left-hand method. I would agree with you. If you just were subbing in one number. But in calculus, we might be subbing in a lot of different numbers, and it'll be easier to get one whole function like we did on the right-hand side. Get it all as one function, then start subbing your numbers in so you don't have to do multiple steps there, saving yourself a little bit of work. Any questions about those 2 orange examples, though, that are so important? I feel like I'm almost done. Am I? I feel like I'm almost done. My thing says 2 more pages, but I'm not sure that's true. No, it's just 1 more page. Page 5 is blank. After a bit of thought, the following idea should. Should. Let's go with could. Shall we? Could become clear. Well, should sort of implies like, oh, this is going to be obvious. Of course. But could is like, oh, we might understand that now. If both f and f inverse are functions, then f inverse at f equals x all the time. What we mean is, if you do the inverse one right after another, if you sub the inverse into itself, you should get the x back a little bit. This one's a bit of a problem because of squared and squaring. So don't write this down as gospel. This is just get the idea. How about if you do log base a and then a to the power right after another, you should get x back. Yeah? If you do root x squared, you get x. Yeah? And that's all that's saying there. But I'm not getting hung on that. I am not red highlighting this. I just mentioned at the end, it's just like if these happen to be inverses, composition cancels itself out. Right? Short homework, page 552, 1 to 3, 5, and 7. Pay special attention to the ones that are just like the orange ones so that you'll be ready for the exam questions on these. Questions there?